Okay, okay, ladies and gentlemen. Ladies and gentlemen, we are doing the last section of Chapter 7, Section 7.8. The topic is improper integrals. Let's get started. Section 7.8, improper integrals. I'm going to introduce this with an example. Suppose we look at the curve y equals 1 over x squared for x bigger than or equal to 1. So that curve, here's x equals 1, is the x-axis. It looks like this. And the question one might ask is this region, which is unbounded, does it have finite area? Well, we can try to make sense of that in the following way. We can cut it off at some number, let's say call it t, this number, and calculate the area from 1 to t, and then let t shoot off to infinity. So let's do that. So let's consider so I'm going to write this symbol. I'm going to define it later, the integral from 1 to infinity of 1 over x squared dx. Think of that as the area under the curve from 1 to infinity. So I'm going to think of this is actually my definition. It's the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. Now, if we integrate 1 over x squared, we find the antiderivative, we get minus 1 over x, and we're evaluating that from 1 to t, and we still have to take the limit, of course, as t goes to infinity. Now, if we do that, what do we get? We get, when we stick in t into the limits of into this antiderivative, we get minus 1 over t. That's the evaluation at t. And when we evaluate at 1, we get minus 1 over 1. So that we're going to take the limit of t as t goes to infinity of this expression. And lo and behold, the term here that's involving the t goes to 0 in this case. So what ends up happening is that we get this first term goes away, and if you do the little arithmetic, you're going to get 1. So that means the area under this curve is 1. That's really what that's saying. So the answer is 1 in this case. So this calls for the definitions. Okay, so there are 3 definitions I'm going to make. In the first case, we assume the integral from some fixed number a to t f of x dx exists for all t bigger than or equal to a. Then we define the integral from a to infinity of f of x dx. This is called an improper integral of the first kind. So the integral from a to infinity of f of x dx is by definition, so I'm going to put 2 dots here, meaning this equality is a definition. It's the limit as t goes to infinity of the integral from a to t of f of x dx. Now, 2 things can happen. If the limit exists, we say it converges the integral. If it doesn't exist, we say it, so if it doesn't exist, so when I say if it exists, I mean it's a finite number. If it doesn't exist, I mean there's no limit, or its limit is plus or minus infinity. It's not a finite number. In this case, we'll say it diverges. So these are the 2 different situations. We're interested in determining what the value of this integral is, but we also want to know if we can't determine the value, we'd like to know whether it converges or diverges at the minimum. Okay, so that's the first definition of an improper integral of the first kind. There's another kind of improper integral of the first kind, which has t in the bottom limit of integration and then some number b at the top of integration. So this is the case so let me in this case we got to assume something. So we're going to assume that this exists for t less than or equal to b, for all t less than or equal to b, and then we'll write the integral from minus infinity to b of f of x dx is equal, this is the definition, the limit as t goes to minus infinity of the integral from t to b f of x dx. So this is the case where you have, say, a curve. Maybe it looks like this, and here's b over here, and you're looking at the area of the region. If the function is non-negative, its area to the left. Okay, and then there's a third case to consider, where we make the same assumptions as in 1 and 2. We can write minus infinity to infinity of f of x dx. And then we will put this as the same thing as the integral from minus infinity to any number. We could take it to be 0 if we want, but I'll put a here, f of x dx, plus the integral from a to infinity of f of x dx. We're just adding the two areas up in that case. So that's the definition of the improper integral of the first kind. We're only going to consider improper integrals of the first kind today. In my next lecture, I'm going to talk about improper integrals of the second kind. You don't have to worry about that today, though. So let's do another example. The integral from 1 to infinity of 1 over x dx. Now this looks innocent enough. It looks very similar to the example we had before, where we had 1 over x squared. But when we do it, this is by definition the limit as t goes to infinity of the integral from from 1 to t of dx over x, which is the limit as t goes to infinity of ln absolute value of x, but t is non-negative here, so we could just put ln of x from 1 to t, and that's the same thing as the limit as t goes to infinity of ln of t minus ln of 1, but ln of 1 is 0, so it doesn't appear, and this goes off to plus infinity, so it diverges, and that's all you can say. So this integral doesn't exist. That's kind of weird, because this area is for the under the curve 1 over x, whereas in the previous case we had a very similar looking curve which had finite area from 1 to infinity. Actually, this calls into question, what about the general case? So let me put that here in the next example. What about the case, the integral of dx over x to the power of p, where p is some real number from 1 to infinity? I'm going to do that on the next slide. Okay, so this example that we're continuing is really the same thing. We can rewrite the exponent in the following way of x to the minus p dx from 1 to infinity. Now that integral is going to be the same thing as the limit as t goes to infinity of the integral from 1 to t of x to the minus p dx. And there, we can integrate this. Now, there are two cases. The case where p is equal to 1 is different, and we already covered it. That would be the case of dx, 1 over x dx, and that would give me an ln of x. So that would be ln of x from 1 to t. And the other case would be x to the minus p plus 1 over minus p plus 1 if p is not equal to 1. So that's what you get, the antiderivative. And that's from 1 to t. Okay, so now we can evaluate this. So in the case p equal 1, we already did that, it diverges. So I'm not going to handle that case. So let me handle the other cases. Okay, so now what happens there? So I'm going to write this as x. So I'm going to take I have to take a limit here, by the way. So it's the limit as t goes to infinity of, I'm going to write minus p plus 1 as 1 minus p. So it's 1 minus p over 1 minus p evaluated from 1 to t. Now, what happens? Oops. Yeah, so it's the limit as t goes to infinity of t to the 1 minus p. When we stick in, substitute t for x, we get 2 to the 1 minus p over 1 minus p. And when we subtract off the value at 1, we get 1 over 1 minus p. Okay, so that's what you get. Now, what is that? Now, if the exponent of t is not negative, so if 1 minus p is not negative, that is, if p is less than or equal to 1, the numerator blows up when t gets big, because the exponent will be positive and not negative in that case. So this is going to diverge if p is less than or equal to 1. Okay, we know it, for p equals 1 it diverges. I'm including that case there. Now what happens if p is bigger than 1? Well, t to the 1 minus p is t to a positive number, and when you stick in larger and larger values of t, t to a negative number, sorry, t to a negative number, strictly negative number, when you stick in positive powers of t, that's going to vanish. And so what you're going to get is, this is going to, this term here, oops, I didn't mean to do that, t to the 1 minus p over 1 minus p, this term here is going to vanish. So what does that tell us? That tells us they're going to get a negative of 1 over 1 minus p, which we can think of as 1 over p minus 1, if p is bigger than 1. So this is the solution to the problem. So the integral converges if p is bigger than 1, the integral of 1 to infinity of dx over x to the p. It converges if and only if p is bigger than 1, and you'll get a value of 1 over p minus 1 in that case. So that's going to come up later in the course over and over. This is a very important integral to work with. Okay, I'm going to clear the screen. Okay, so let's try something like this. The integral from minus infinity to infinity of dx over 1 plus x squared. Okay, this is, this can be written if we want to. I'm going to choose a value a. A will be 0 in this case. So it's going to be the same thing as the integral from minus infinity to 0 of dx over 1 plus x squared, plus the integral from 0 to infinity of dx over 1 plus x squared. Okay, now that's the same thing as the limit as t goes to minus infinity of the integral of t to 0 dx over 1 plus x squared, plus the integral for the limit as t goes to plus infinity of the integral from 0 to t of dx over 1 plus x squared. Now the antiderivative of 1 over 1 plus x squared is the arctangent function. So we're going to get the sum of these two limits we have to compute. Okay, so now what happens to the arctangent function? One way to understand the arctangent function is to look at the tangent function, what it's doing. So the arctangent function is the inverse function to this branch of the tangent function, this is tangent x. So now what happens when t goes to minus infinity of the arctangent? That's in this direction. That's at the value minus pi over 2. So what this is the arctangent of 0 is 0, and the arctangent of minus infinity is minus pi over 2. So I'm evaluating, I get minus negative pi over 2. So this first thing is going to be giving me a pi over 2 contribution. Similarly, the second expression, as t goes to plus infinity, the arctangent is going to tend to pi over 2, because the tangent of pi over 2 is in plus infinity. So this is going to give me a pi over 2 minus the arctangent of 0, which gives me another contribution of pi over 2. So we have to add these together, and we get a value of pi for the answer. How sweet. Okay, so I'm going to do one more problem. So the last problem I'd like to do is the integral from minus infinity to 0 of x times e to the x dx. Okay, so what I'm going to do is I'm going to first do the corresponding indefinite integral over here, the integral of x e to the x dx. How do you do that? Well, remember, there's an integration by parts. U equals x, du equals dx. So dv equals e to the x dx. So v equals e to the x. So you're going to get u times v, which is x e to the x, minus the integral of v du, which is the integral of e to the x dx. And then this becomes x e to the x minus e to the x plus c. Okay, so what I can do then is this is the integral, the limit, it's a limit, so I have to put a limit in. It's the limit as t goes to minus infinity of the integral of t to 0, from t to 0 of x e to the x dx. I can take my antiderivative. I'm going to take the constant c equal to 0 here. I'm going to get x e to the x. I'm going to take the limit as t goes to minus infinity. X e to the x minus e to the x, evaluated from t to 0. And then, so if we stick in, so that's going to give me the limit as t goes to minus infinity. So if I stick in 0, first of all, 0 times e to the 0 is 0, minus e to the 0 is 1. That's the value at 0. And the value at t is t e to the t minus e to the t. Okay, so let me do a little bit of simplification. This is the same thing as the limit as t goes to minus infinity of what? Of 1 minus t times e to the t minus 1. Okay, so we have to compute this limit as t goes to minus infinity. So the 1 is really not a big deal. It's the first term that matters. So I'm going to write 1 minus t e to the t as, and I'll explain why, as 1 minus t over e to the minus t. The reason why is I'm going to use L'Hopital's rule. If we let t go off to minus infinity, both top and bottom become an indeterminate form of type infinity over infinity. So that means by L'Hopital, this is the same thing. This limit is the same thing as the limit of the derivative of the top, which is minus 1, over the derivative of the bottom, which is minus e to the minus t, which is the same thing as, of course, e to the t. Now, what happens to e to the t as t goes to minus infinity? As t goes to minus infinity, this vanishes, which tells me this first term here in the limit is going to go away as t goes to minus infinity. So the answer to this is going to be minus 1, it looks like to me. And very well, I guess that's it. And that's it. Let's call it a day. Okay.